Hi folks, welcome back. We start today talking about, well, the next part of electrostatics, which has to do with fields. And this is a topic where it starts to get tricky for a lot of people. So what I try to do here is draw some parallels between gravitation, which people tend to have a pretty good handle on, and electrostatics, which can get what seems to be a lot more abstract. So we'll start with the gravitation side of this analogy. And let me see if I can get rid of this stuff. Oh well. So what we say is let's take some distance away from this mass m. We'll call that distance r. So here's r. And if we were to say there's a mass here that I'll call lowercase m, well, we should be comfortable right now with the fact that the large mass exerts a gravitational force Fg on that red mass m. Now, let's say we had a different mass here. I'll make it, say, a smaller, again, that's a lowercase m. We're going to have a smaller force here. Well, I should really make it green just like the other one. Right? It's the green big mass pulling on the little mass. All right, now, hopefully if we think back to gravitation, we can quantify this force. Up top here, we're going to have that Fg is g times big M times this little m over r squared. Should look familiar, just like the electrostatic force with charges. So here's, again, Fg is g times big M times that little m over the same r squared. All right, so those forces are different for sure. However, there's something that's the same, and it's not, well, what we have to do is really eliminate the mass. Those two masses are different, right? But if we do this, divide by the mass, divide both sides by the mass, well, that does that. Here, if we divide this by the mass, we get that. Now notice that each of these expressions, gm over r squared and gm over r squared, are the same. All right, so what we've just defined is this quantity that is force, gravitational force per unit mass. And we said that's equal to g times m over r squared. Well, hopefully you recognize this, and you might even go as far back as to recognize that. You know, we know that we've said Fg is mg. So Fg divided by mass is g. So we've called that gravitational acceleration in the past, but the one way that we also mentioned thinking about that is it's also literally what's called gravitational field strength. And the nice way to think about it, for me at least, is if we look right from here, we have a quantity that's measured in newtons for force per kilogram, right? Force per unit mass. And if we went through and looked at the units from gm over r squared here, we'd see that that quantity, you know, again, if it's Earth, near the surface of the Earth, we end up with 9.8 newtons per kilogram. But this gives us an expression to find the gravitational field strength anywhere at any distance away from the Earth. Okay? Now, if we take this analogy to electrostatic stuff, oh yeah, now here's the deal. Gravitational field is a vector. Real important. The tricky thing is it's not a force. All right? We would say that what we say is that at this location right here, and I'll just call this location X, there exists a gravitational field G that's equal to, well, it has a magnitude gm over r squared, right? And the strength of that field is what dictates how strong the force is that'll be exerted on any mass if we place a mass there. But regardless of there being a mass at the location or not, at that location, there is a certain gravitational field strength. Right in front of me at some place in space, the gravitational field strength is 9.8 newtons per kilogram, and it points towards the center of the Earth. Okay? Okay. Now, on the electrostatic side, what we have, now let me just go back here. Yeah, so, I'm sorry. So, we're kind of really getting at this question, right? No matter where we place a mass, it will experience a gravitational force, and that's because there is a gravitational field that exists everywhere around mass M. All right? Now, if we go here, it's the same thing, except now we're not dealing with mass anymore. Now what I call our fundamental entity here, now it says no matter where an additional charge is placed, it will experience an electrostatic force. And why? Well, the answer to that is because just like around every mass there's a gravitational field, well, here around every charge there's an electric field. All right, so if we go back to the sort of same analogy we had before, that's not quite good enough. But if we say at some distance r from that charge, well, if we put one, let's call this Q here, and I'll call it a positive charge, and I'll say that this is a positive charge also, okay? And then here, well, so our little charge, little Q out here, would feel a force that points like that, Fe, where Fe would be K, big Q, little q, over r squared. If we have a separate, different charge, and I'll even make this one a negative, now this one would feel a force this way that might be a different strength because the green Q and the blue Q might not have the same magnitude, but we know that this force is K, big Q, little blue q, over the same r squared. Right? So those forces very well might be of different magnitudes. However, just like we did before, if we take this one, divide by our charge, well, that does this. And we take this one, divide by our charge, and we get that. Well, we get that expression. We've developed this expression that says there's some quantity force per unit charge, which is equal to K times big Q over r squared, right? And that's what we call electric field. Now, the real tricky thing about this is that field starts with F, and force starts with F, and that's the thing that people have the most trouble with in this part of the unit. All right, just a naming thing. All right, so E, capital E, I always end up saying electric field to remind you that that's what we mean by capital E. Okay, so if you look back to the last slide, we have gravitational field strength. That's gravitational force per unit mass. Now we have electric field. That's electrostatic force per unit charge. So you notice it's going to be measured in here, force per unit charge, newtons per coulomb. All right. If you went through this expression here, using the units of K, using coulombs for Q, and using meters for R, you'd get the same thing, newtons per coulomb there. All right. Now, a big thing to mention is what's the difference between big Q and little q. All right. So what we say is big Q is charge that makes a field. And little q, I say, is charge in a field. Now, does that say that little q doesn't make its own field? No, it doesn't say that. All right? Every charge makes an electric field, just like every mass makes a gravitational field. But what we talk about is if we use this expression here, this allows us to find the strength of the field made by charge capital Q. Right? If we use this expression here, it allows us to calculate the force exerted on charge little q that's in a field that was made by charge capital Q. So that's why those two expressions are related, with the little q in one and the big Q in the other. That's another very tricky thing. All right, these are both charges. They're both certainly measured in coulombs. So yeah, a couple different ways to quantify electric field strength. All right, now here's a tricky thing also. And you notice that the thing with gravitational forces is they always point in one direction, right? Things only attract, masses only ever attract each other, but charges can attract or repel each other depending on the sign of the charge. Mass, there's just mass. Charge, there's positive charge and negative charge. So what we have to do is make this convention. And here's our convention. The convention is the electric field points in the direction of the force that a big deal positive charge placed in that field would experience. We'll say that again. Electric field points in the direction of the force that a positive charge would experience. So we're not saying that field and force are the same thing, but they can point in the same direction. All right, the convention for electric field is that it points in the direction of the force that a positive charge would feel. So notice, our little green charge up here, the force that it feels is away from our big positive red Q. That means that by definition, at that location where the green Q is, electric field points up and to the left. All right, at, say, this location right here, location X, which is not a charge, that's just a place in space. The electric field would point away from that positive red charge. I should do it in red. Because if we were to put a positive charge at that location, it would be pushed away from our big red positive. Okay, so there's a little convention about electric fields. So we'll nail down some basics here. First and foremost, no matter where we put at any location around this red positive charge, if we were to place another positive charge there, it would be pushed away from the big red one. That means that anywhere around here, we draw the electric field like this, that it points away from that charge. This is how we draw an electric field around what we call a point charge. Now, assuming that this negative charge is, completely isolated from the positive charge, again, if we want to know the direction of the electric field near this negative blue charge, we imagine putting a positive charge anywhere near it. If we put a positive charge here, well, that charge would be pulled inward toward the negative. If we put a positive charge here, it would be pulled inward toward the negative, and so on and so on. So that defines the convention for electric field direction, right? We already said, sure, it points in the direction of the force that a positive charge would feel, but we can simplify that maybe to say electric fields point away from positive charge, and electric fields point toward negative charge. Always. All right, now, you ought to be able to do a little qualitative analysis of electric fields just by looking at pictures of their drawings. How can you tell where the field is strong? Well, hopefully it sort of makes sense to you that the closer you are to a charge or a mass, the stronger its field. For a charge, it's electric field. For a mass, it's gravitational field. So hopefully that part makes sense. And if you notice, if we look near the charge, I'm going to define, this is what I'm defining as my unit area. Completely arbitrary. But inside that unit area, we say there are 2 lines per unit area. So we can talk something about what we can talk about something we call electric field line density. How many lines there are per unit area, all right? In that case, there are 2 lines per unit area. If I go, say, out here with the same unit area, now we only ever get a maximum of 1 line per unit area. All right, if we get even closer, if I did my unit area in here, we might be able to sneak 3 lines per unit area in there. All right, so fields are strongest where the lines have the greatest density, or where they're closest together. So we'll see from time to time some pretty crazy looking electric fields. You can tell where they're strong by where there are lots of lines packed closely together. All right, and where they're weak, where there are lots of lines that are spread far apart. Now, fields end. What I'm getting at is, how far out do these fields go? All right, well, the deal is, I should just add a word, fields never end. All right, if we look at E equals KQ over R squared, well, as R approaches infinity, E approaches 0. Right? But R is never really infinite. Okay, so no matter how far you are away from a charge, there is some value of electric field strength. All right, it might be small, but it's there. So fields never end. Field lines go into infinite space. Okay, now a couple of, you'll recognize this slide. It looks a lot like one we did with forces, but now we're saying, let's not find the force on a charge. We're finding the direction of electric field at a location. So this thing here, well, it's not a thing. It's a place, right? That's a big deal. It's not a charge. It's not an object. It's not a mass. It's nothing. It's just a location in space. All right, so if we look at the field created by the green charge over here, well, that's a positive charge. Fields point by definition away from positive charge. We'll call that E3. The red 6 Coulomb charge over here is a negative charge. Fields by definition point toward positive charges, E6. And I know, because it goes as KQ over R squared, if this 6 Coulomb charge is twice as strong as the 3 Coulomb charge, it's going to make a field twice as strong. That's why this vector here is twice as long as the green one. Right? So our E net here, E3 plus E6, because they point in the same direction. If we wanted to be technical about it, we do this. They're vectors. Let's see, we switch the signs of one of them here, so I have this 3 Coulomb charge is negative, fields point toward negative charge. This 6 Coulomb charge is positive, fields point, the 6 Coulomb charge is also negative, fields point toward negative charge. And now our net electric field looks like this. Okay, I'd call that E6 minus E3 because they point in opposite directions. Now, where's there a place where the net electric field is 0? Well, let's see. If we go, say, well, you ought to pause, maybe. See if you can figure out the answer. Go ahead, pause. Okay, so somewhere in here, we're going to have, oh, that's not going to work. It's really going to be somewhere over here, isn't it? So if we go somewhere over here, we're farther away from a stronger charge. Stronger charges typically make stronger fields, but when you're farther away from them, their fields are weaker. So we'll call that E6. Over here, weaker charges typically make weaker fields, but we're closer to this one, so it could be the same thing. So somewhere over here, right of the midway point, we can get those two fields to be equal and opposite, and therefore a net electric field of 0. Some two-dimensional things, these, we get a field like that. field like that, and therefore a net field like this, right? Where we, excuse me, we would Pythagorate, right, to find that, to find our net field. You should try the next couple yourself. We get a field toward positive, sorry, toward negative, a field away from positive. So we Pythagorate, we get something like this. Last one, we're away from positive, we're toward negative. We get a net field that looks like that. Okay, so we will we'll work on problems when we get back into class tomorrow. All right, but you know, there's the nice thing right now. There's only two equations you need that can quantify electric field strength, right? So you should be comfortable with those equations, and yeah, we'll pick up there tomorrow. Thanks.